Today we're diving into the fascinating world of random isotropic fractals, using the ideal polymer chain as our main example. Fractals are objects that display self-similarity, meaning their structure looks similar at different scales. Polymers, which are long chains of repeating units called monomers, are a perfect real-world illustration of this concept. By exploring how these chains behave, we'll uncover the mathematical beauty behind their structure and how randomness plays a role in their formation. Ideal polymer chain is a theoretical model where each monomer is connected in a sequence, forming a flexible chain. Each monomer has a fixed length, often denoted as a. The chain's configuration can be described as a random walk, where each step is independent and has the same length. This randomness means the chain can fold and twist in countless ways, making its overall shape unpredictable but statistically describable. Imagine taking a series of steps each in a completely random direction. This is the essence of a random walk. In the context of polymers, each monomer represents a step and the entire chain is the path traced out by these steps. Because the directions are uncorrelated, the average position after many steps tends to return to the starting point, but the actual path can be quite convoluted. For a random walk, the average vector distance from the start to the end of the chain is 0. This means that on average the chain doesn't favor any particular direction. However, the mean square displacement, which measures the average squared distance between the first and last monomer, grows with the number of steps. Specifically, it's proportional to the number of monomers times the square of the step length. Radius of gyration, or RG, is a key measure of a polymer's size. It represents the average distance of the monomers from the chain's center of mass, weighted by their positions. For an ideal chain, the radius of gyration squared is approximately equal to the number of monomers times the square of the bond length. This gives us a simple way to estimate the overall dimensions of the polymer. Mathematically, the radius of gyration is defined as the square root of the weighted average of the squared distances of all monomers from the center of mass. For an ideal chain, this calculation simplifies nicely, showing that Rg squared is proportional to the number of monomers times the square of the bond length. This formula is widely used in polymer physics to describe chain dimensions. One of the most fascinating aspects of polymers is their self-similarity. If we group several monomers together and treat them as a single segment, the overall structure of the chain remains statistically the same. This property means that at different scales the polymer looks and behaves similarly, a hallmark of fractal objects. See how scaling works in practice. If we group p monomers into one segment, the number of segments becomes n divided by p, and the new segment length is the square root of p times the original length. When we recalculate the radius of gyration with these new parameters, we find it remains unchanged. This demonstrates the self-similar, scale-invariant nature of the polymer chain. This invariance under scaling is what makes the polymer chain a fractal. No matter how you zoom in or out, provided you stay between the size of a monomer and the overall chain, the statistical properties remain the same. This is a defining feature of fractals and is central to understanding complex polymer behavior. To analyze how monomers are distributed within the polymer, we use the radial distribution function g(r). This function tells us how many monomers are found at a certain distance from a reference point, normalized by the volume of a spherical shell at that distance. It's a powerful tool for understanding the internal structure of the chain. Radial distribution function is calculated by dividing the number of monomers in a thin spherical shell at distance r by the shell's volume. For an ideal chain, the number of monomers within radius r scales as r/a2. This leads to a simple expression for gr, showing how density changes with distance. For distances smaller than the radius of gyration, the function gr is proportional to 1. This means that at these scales the polymer's structure is self-similar. The same statistical patterns repeat regardless of how closely you look, as long as you're within the appropriate range. If we plot gr against r, we see a curve that decreases as 1r for distances less than the radius of gyration. This visual representation helps us understand the self-similar fractal nature of the polymer chain. The plot is a direct reflection of the underlying mathematics and physical structure. Sum up, random isotropic fractals like ideal polymer chains exhibit self-similarity, scale invariance, and fractal behavior. The radius of gyration and the radial distribution function are essential tools for describing their structure. These concepts not only deepen our understanding of polymers, but also connect to broader ideas in physics and mathematics. Understanding the fractal nature of polymers has practical implications in materials science, biology, and nanotechnology. These principles help scientists design new materials, study biological macromolecules, and explore the properties of complex systems. The study of random isotropic fractals continues to inspire research and innovation across multiple fields.